Hello everyone. Thank you for giving me this chance to talk about the freeze drying. And today my topic is design of freeze drying process for drugs. And through my speech, I hope that all of you could design the freeze drying process and know about freeze drying process. So today I talk about 3 parts. The first is basic principles of freeze drying. And second is general process design for drug freeze drying in Tofflon lyophilization lab. And third is cases of problem solving in freeze drying design for pharmaceutical industry. So I list some cases. Okay, first let's talk about the basic principles of freeze drying. And somebody may ask, what is freeze drying? So generally, I want to say about simply, just like this equation. Now, I said freeze drying is equal to freezing plus drying. So the first step is freezing, and the second step is drying. So it's simply 2 steps are included here. And so why freeze drying are used? Generally speaking, I think several parts are important, but I list some of them. The first is through freeze drying, we can get a good shape of the product. The second, we can get a good color. And the most important is the third one. We can get the long-term preservation of the drugs. So let's watch the flash in the right. Now this is a vial of liquid. So the first step, I decrease the temperature, go to the freezing step. Now the solid become to the liquid become to solid. This is the freezing step. And second, we decrease the pressure. So give it a vacuum environment. So let's begin. We can find that the frozen layer appeared. The top of the product becomes the frozen layer, and the down of the vials is also the frozen. Is also the liquid. Is also the frozen layer. A dry layer. A dried layer is appeared. So as the time going on, all of the frozen layer become to dry layer. So that is the whole process of freeze drying in the flash. So let's see the next picture. This picture is more clear. We can divide the process into 2 sections. The first is freezing in the left. Now the left is liquid to solid. The liquid is frozen. And the drying step, we divide the drying step into 2 steps. The first is primary drying, and the second is secondary drying. The primary drying is used to remove the free water, and the second drying we use to move the bound water. So the water exists in the product in 2 states. Now this picture shows the same thing as the last flash. After the freeze drying finished, we sealed the vials. So somebody may ask, why can we perform this freeze drying? We answer this question. We must talk about the water. So this is the water phase diagram. The abscissal axis is the temperature axis, and the vertical axis is the pressure axis. Now 3 phases here: the liquid, the solid, and the gas. So everything is in 3 states. The water, so is water. And this arrow, the black arrow, is a triple point. Now we go into the first step, freezing step. At the same pressure, we maintain the pressure at same value, so we decrease the temperature. Now as the red arrow, the liquid become to solid, so the water become to ice. And second, we maintain the temperature at the low level in the same value and decrease the pressure. So give it a vacuum environment. there's no phases changes. But we go into the third step. We increase the temperature at the same pressure as the vacuum environment. Now we found that the solid become to gas directly. So this is the whole freeze drying process. We talk about the water. The next, after we talk about the water, we must go into the next, the drying step. But drying step have different effect. So how did this effect appears? Now we must talk about the freezing, because the freezing steps can give us two states. The drug solution in two states. When we decrease the temperature, we can get the crystalline state or the non-crystalline state. The non-crystalline state is also called glassy state. For example, the crystalline state, the sodium chloride, just the salt. When we decrease temperature, the sodium chloride solution will become to crystalline state. Now please see this four picture on the right. Now the structure is the crystalline structure. It's very clear. The non-crystalline state, for example, the sucrose solution, just as the right picture down of the this picture, that we see that there's no crystalline structure as up four pictures. So we call it glassy state. In the glassy state, there's no crystals appeared, but the glassy state is just between the solid and the liquid. There's difference between the crystalline state. So these two states give when we perform the freeze drying, so that is different. We perform with different method. So let's go into next. Just now I said the water exists in the product in two states. The first is bond water, and the second is free water. We can find that the free water exists in is the most water in the product, and the free water was removed in the primary stage. The bond water, just as we see, is is smaller. We found that it was removed in the secondary drying stage. So let's go into next. Today I want to talk about how to design a freeze drying cycle. So there are a lot of parameters to be controlled in the freeze drying design. We can talk about it in three steps: the freezing step, the primary drying step, and the secondary drying step. As we see, as this table shows us, the freezing steps, we control three parameters: the ramping rate, annealing or not, and the freezing temperature. The ramping rate is very important. Different ramping rate give us the different structure of the products. So just as the crystalline structure or the glassy structure. And another, annealing or not. Annealing may give us a uniform structure, and some products need annealing. If we don't do this annealing, so we can't get the good product. But some products do not need annealing. And the third one is freezing temperature. The freezing temperature is not proper. If the freezing temperature is not proper, we can't get a good freeze drying cycle. So the three parameters are important, but they are not the most important. The most important parameters are included in the primary drying and secondary drying, as shown in this table. The primary drying, the first collapse temperature. The collapse temperature I will talk about later. Just see the first three temperatures: collapse temperature, eutectic temperature, and glass transition temperature. Both three temperatures are need to control the temperature of the primary drying. As the most important parameter was included in the primary drying and secondary drying. The first three more important parameters are collapse temperature, eutectic temperature, and glass transition temperature. These three temperatures I will talk about later. But this temperature is very important. We control this temperature in primary drying. If this temperature is not controlled well, we can't get a good product. So we can't control the water content in the product, in the final product. And the second is the pressure rise. The pressure rise is used to determine the end of the primary drying or the secondary drying. So it's also very important. It can reduce the time of the freeze drying cycle. Another dew point. Dew point is the same effect of as the pressure rise. The last vacuum degree is also very important. It is just determine the mass and heat transfer of the product. In the secondary drying, also the temperature of the drug degradation. Now in the secondary drying, we increase the temperature to a high value, to the high value that the drug can endure. If the drug can endure, we can increase the temperature to that value. Also, the pressure rise is also the same effect as the pressure rise in the primary drying. So, just let's talk about collapse temperature. So, what is collapse temperature? Before talk about this, we must talk about the two states, the crystalline states and the non-crystalline states. The crystalline states, just as I said, if we decrease the temperature, the crystal appears. The structure of the crystal appears. So when this process happens, there is a temperature. We call it eutectic temperature. When the liquid becomes to solid, that is the point. At this point, the latent heat was released, so we call it eutectic temperature. As another non-crystalline state, we call it glassy state. In the glassy state, when we decrease the temperature, the liquid become to glassy state, not the solid. At this process, there's no latent heat released. So we determine this, we call it solidification. So we determine this temperature, glass transition temperature. We can't use the same method as the crystalline state. We just use the electricity resistance method, because electricity resistance are changed at that point. So the eutectic temperature and the glass transition temperature are nearly the same meaning when we design the freeze drying cycle. But determining these parameters are very difficult, and we don't use this. Commonly, we don't use this eutectic temperature and glass transition temperature. We use collapse temperature. So what is collapse temperature? Let's see next picture. Now, just this picture, we can consider the product, the drug solution, as this. Now there is the pore here, and the yellow layer is the drug, and the blue layer is the ice. When we go into the drying process, the ice sublimates through the pores. Now we increase the temperature. If we increase the temperature, let's go to the right, we can find that the yellow layers, the structure of the yellow layers changes. Now as we increase the temperature, continues. Now the layer of the drug changes much. So the pore of the waters was blocked up, so the water cannot be removed through the pores. So this is the collapse temperature at that point. When the water was not removed directly, so we can't get the product, a good product. At this point, we call it collapse. So we cannot make the product collapse. So this is a very important parameter to be controlled. But how to determine the collapse temperature? As these pictures, this is a freeze drying microscope. We put 2 milliliters of the samples onto the FDM, and through the computer screen, we can see a picture and videos to determine the collapse temperature. This FDM, we can just consider it as a smaller water was removed. Just this process happens at the border of the product. Now the light black layer is the frozen layer. Now the light frozen layer, light black layer is the frozen layer. So when we go into the drying process, the two layers appears, and there is a sublimation font. Now you can see this sublimation font. So we increase the temperature now. As temperature going on, the sublimation font. The sublimation font going from the left to right. And at some point, just like the right picture, a white point appeared. Now we call it collapse. We call it collapse. As time going on, the collapse more. So we can't make the product collapse. So we can't make the white point appeared. Now this is the collapse temperature. The collapse temperature is the safest for the primary drying process. Now let's see a video. Now this is the video of Y sign. Now we decrease the temperature. At some point it becomes too solid, just white to black. Now the border is a dried layer. We increase the temperature. As time going on, now the dried layer become larger, and sublimation font goes from left to right. We increase the temperature. Please notice this font. Notice here. Now the white point appeared. We call it collapse. We just call it collapse. As the time going on, all the products collapse. So collapse temperature is the safest for primary drying. And we must control the collapse temperature in the first drying cycle design. The next important parameter is pressure rise. So what is pressure rise? Before talk about this, we must talk about the vapor movement in the freeze drying equipment. And just look at this picture on the left. Now this is the freeze dryer. Now here is the front chamber. This is the back chamber. There's a cold trap in the back chamber. The temperature in the front chamber is different with the back chamber. Just the vapor can move from the front chamber to the back chamber, just because of the pressure is different. Now just see the right table. Right table says the vapor, saturated vapor under different temperature. Now in the front chamber, the vapor is high, and in the back chamber, the vapor is low. So the difference of pressure makes the force of the vapor movement. So with the vapor movement, we can remove the water continually. So we can express this force as this equation. So delta P is P1 minus P2 minus P3. Now P3 is the resistance between the front chamber and the back chamber. That is the channel. Now, how to determine the pressure rise? Just look at this picture. There is a septal valve in the channel between the front chamber and the back chamber. So when we think about the drying process ends, we now turn off the septal valve. So if the water also exists in the product, so it can sublimate continually. So the pressure may rise fast. If the water is nearly removed, or the pressure may not removed very fast. It's very slowly. So just look at this right square and this here. We think this is a freeze drying curve. At this 2 point, the pressure rise. If we found that the pressure rise is not higher than 0.5 Pascal per minute, we think about the drying process may end. So that is pressure rise. Now next, after we talk about the 2 important parameters, we also talk about the other important thing is the mass and heat transfer. If we want to get a good product, we must know the mass and heat transfer of the product. If we put our vials on the shelf of the freeze dryer, there are 3 cases of mass and heat transfer. Just as the left, the heat is conducted from the shelf through the frozen layer. So on the interface of the dry layer and the frozen layer, the heat is abstract from the frozen layer. And the second, the heat is from the radiation, from the shelf radiation. Now the third one, both of the 2 mass transfer exist. Now this equation shows the sublimation rate of ice, and G is equal to PIW plus minus PA and divided by RD and RS plus RL. Now this is the sublimation rate. We found that the denominator has 3 parameters. Both 3 parameters are the resistance of the freeze dryer. The next is the heat transfer of flux through frozen layer. The frozen layer is also here. We express this. And the next, heat transfer flux by the thermal radiation. Now the 3 cases, 2 cases of heat transfer. So if we put some product on the freeze dryer, we usually consider about the mass and heat transfer. It's also very important. So after all, we talk about the freeze drying cycle. Now, if we give you a report, it's just like this, on the left, at the right curve, is a freezing curve. Now we decrease the temperature. And at this point, the latent heat was released. Just as look at as solidification. The liquid becomes too solid. And at this point, we decrease the pressure. Now, as a blue curve, we decrease the pressure. So we go into the drying step. Now this part is the primary drying part, and this part is a secondary drying part. Now at these squares, we determine the pressure rise test. We can see the shelf control temperature. This temperature depends on the collapse temperature, and this temperature secondary drying steps, this temperature depends on the temperature of the property of the drugs. The drugs can endure. So let's go into the next part. After we talk about the basic principles of freeze drying, and we want to show you about the general process of design for drug freeze drying in Tofflon lyophilization lab. So how to get good freeze drying products? We think three things are needed. First is good freeze drying cycle, and the second is good equipment, and the third one is good formulation. So today I want to talk about the first, good freeze drying cycle. How to get a good freeze drying cycle? Several steps are needed. First, we must know the drug property. So we must analyze the drug property, the solubility, the pH analysis, stability under different temperature, molecular, and H bonds. Now these are also important. We must prepare the drug solution properly. If we don't know this, we usually don't know how to design freeze drying cycle. There may be some problems appeared. So the second step is the formulation design. But if that it depends on our clients. If clients needs these steps, we do the formulation design. If the clients don't need this, we usually don't do this. The formulation design is usually also important. This formulation includes four steps, 4 parts. The first is buffer. Usually you put some chemicals in the drug solution. The chemicals could adjust the pH of the drug solution. For example, EDTA, folic acid, and so on. This is just as a buffer. And the lyoprotectant, it can protect the drugs, the main drugs. And the third one is the bulking agent, mannitol, lactose, gelatin, and so on. And the third one, antioxidant. So this 4 functional chemicals, we design the formulation. And the third step is the parameter determination. Parameter, usually the collapse temperature, or the eutectic temperature and the glass transition temperature. We commonly determine the collapse temperature. And the last 2 temperature we use just rarely. The 4th steps is the experiment design. Just to design the freeze drying cycle, we must consider several parts: the cooling temperature, the ramping rate, temperature controlled in the primary drying, and the pressure controlled. The cooling temperature, I said just now, the cooling temperature usually, first we must make sure that the temperature can give us the solid of the product solution. If the liquid can't become to the solid, so we can't go into the freeze drying. So cooling temperature, we must make sure the liquid can become to solid. And ramping rate, the ramping rate can give us a good structure of the drug solution. So usually ramping rate, if we we perform the fast cooling or the slow cooling. The fast cooling could give us a large crystal usually, and the slow cooling will give us the small crystal and a more uniform structure. That is difference. So ramping rate must be controlled. And the third one, temperature controlled in the primary drying and secondary drying. So that depends on the collapse temperature or the property of the drugs. Now the third one, the fourth one, pressure control. Usually, we we can put several gas, for example, air into the freeze dryers to control the mass and its heat transfer, just as I showed. Now the fifth one, result analysis. After we performing the experiment, we must examine the product by these 5 parts: color, turbidity, moisture, organic solvent, crystal form. Usually different clients needs different requirement. The color, usually when they perform a freeze drying process, they didn't have the good color. So through the freeze drying process, we can give the color that they need. The turbidity, the moisture often when you don't perform the right freeze drying cycle, so you can't remove the water, or so the moisture is often needed by the client. And the fourth one, organic solvent. When there is some organic solvent in the drug solution, it is often difficult to remove. So you must control the parameter to remove the organic solvent. And the fifth one, crystal form. The crystal form, usually some clients needs the special crystal form of the product. We also can control the formulation or the freeze drying cycle to form the different crystal form. So I know that is different, but we can perform this, and usually we can try it. Now, the second part of this, the service of Tofflon Lyophilization lab. So that is service of my lab. 2 parts. The first is parameter determination. The parameter, just usually, commonly, the collapse temperature. And the second, lyophilization cycle design. Just as this tree. When the clients deliver some samples to us, and we got some samples, and go into the parameter determination process. If the client needs the electricity resistance of the to determine the eutectic temperature or the glass transition temperature, we just perform this as the client said. And usually we determine the temperature by DTA and FDM. FDM is used to determine the collapse temperature. Now this is the parameter determination. And finally we will give you a report. And the second service is the lyophilization cycle design. Now we can see this tree. And when we accept the sample, and we go into the sample acceptance, freeze drying technology analysis, and the experiment design. So next, preparation of the drug solution and the parameter determination. Parameter determination is also included in this service. Then freeze drying equipment and result and analysis. So after we performing a good freeze drying cycle, we will give you a report of the service. Now, this picture shows the products of the Tofflon Lyophilization lab. The chemical drug, biological drug, nano drug, and the hemostatic pasta, and the film, freezing in plate and tablets. All of these products are made in our lab before. So the second part is finished. Let's go into the last part. The cases of problem solving. Now in this part I list several cases of the problem solving that met in our lyophilization lab. So just see these pictures. There are 4 valves here. The left one and the right one is not good. They don't have a good shape. The drugs was shrinked. And the middle two one, we consider it good and just okay. The second one is very good. It's not shrinked, and the shape of the drug is very well. So through the freeze drying cycle, we want to get this one, good one. The case 1, the white sign of bronchitis effect by chicken. And that is the cases our clients gave to us. The problem is moisture is high after freeze drying and shrink the cake. When the clients perform the freeze drying cycle, the moisture, they can't decrease the moisture, and the product, the cake of the product is not very good. It's shrinked, just as this one. So through the freeze drying cycle, we can solve this problem. The key point of this problem is slow cooling. But also, this is a special case. Not all of these problems are dealt by the slow cooling. Now, this first picture is a collapse temperature determination picture. The collapse temperature is minus 30 degrees. Just as this table shows us, the design temperature is minus 45 degrees, and the temperature and the time to the temperature, we need 120 minutes. So that is very slow. We decrease temperature in 120 minutes. That is slow cooling. Through this process, we can get the structure of the product that we need. This is a report of our Tofflon lyophilization lab. Now, this is a picture of the product. We can see that all of these products are very good. Now we analyze why we can get this product. And cooling rate has great effect on size of the ice crystal. Fast cooling helps the water to form large crystal. And the slow cooling promotes the water to form small crystal, which makes the structure more uniform. Now we use the slow cooling, so we make the water form small crystal. The structure is more uniform, so we can get that product with good quality. If we do the fast cooling, maybe we can get the shrinked cake of the product. The shape of the cake depends on the structure of the ice. That is, the second case is omeprazole. There is a problem. The problem is also shrink the cake and the too long cycle time. When the clients perform this freeze drying cycle, they can't get the good product. To solve this problem, the key point is also annealing. We perform annealing. Now we show this problem by the several tables and pictures. Just as this table said, that is a regular freezing process. Now, as we see, the temperature decreases from the minus 14 and to minus 41 centigrade to determine the collapse temperature. Now, these 6 pictures, we found that the collapse appeared at the beginning of the increasing the temperature. When we increase the temperature, the collapse appears. So that is not good for the freeze drying cycle. We must don't use this method. Use the next. Now we are performing the annealing process. Annealing process, just as this picture shows. First, we decrease temperature to minus 45 degrees, and then increase the temperature to minus 15 degrees. And the second, we decrease the temperature again to 45 degrees centigrade. Now that is annealing. Through this process, just as the sixth picture shows us, the picture is different. We found that the collapse did not happen at the beginning. It happens at some point. So through the annealing process, we increase the temperature we increase the collapse temperature. So that is very important. When the collapse temperature was increased, we can increase the temperature controlled in the primary drying, so that can reduce the time of the freeze drying cycle. Now this is the freeze drying cycle table. Now that is cooling process, very important, to minus 45 centigrade. This is the report. So the value of the collapse temperature depends on the drug's property, the formulation, and the cooling method, and so on. The collapse temperature is not a fixed property of the drugs. The formulation, the cooling method, both can affect the collapse temperature. So that is not a fixed value. So we can change it by some method, especially in the freezing process. Annealing may have good effect on enhance of the collapse temperature. So if the collapse temperature can be enhanced, that is very good. The case 3, clogging. In these cases, the problem is per shape. The product is not with good shape, it's per shape. The key point is also cooling rate. We control this parameter to get a good shape of the product. First, let's analyze this problem first. This client need to freeze drying this product not in vials but in plate. So heat transfer is a big problem on freeze drying on the plate. In the plate, temperature is usually different at different point of the plate. In the point near the door, the temperature usually is higher, and in the center of the plate, the temperature usually is very low. So the temperature is different. The temperature difference may promote the big ice crystal, which has great effect on the shape of the cake. So if I want to get the shape, good shape, we must consider this mass and heat transfer, especially the heat transfer on the plate. And this is the report. Now we deal this problem also through the method of slow cooling. Now this is the key point. We're cooling very slowly. Now this is 3 picture of the product. Slow cooling may give us a very good structure of the product. It can, because through the slow cooling, all the products on the plate could abstract the heat slowly. So the difference between the different points of the plate may reduced to a smallest value. So we can control the temperature difference through the slow cooling. The case for vacuum bread. So this problem is the liquid is muddy when dissolved in the water after freeze drying. First, we try several freeze drying cycles. We try several cycles. but we did not deal this problem. So we must get into the formulation design. We must redesign the formulation. This problem, let's see the formulation. This table shows us the formulation. Now this is the initial formulation, and the next is the final formulation redesigned. We can see that the buffer, the concentration of the buffer is a little high, and we consider that the concentration of buffer is high, so we can reduce the concentration to make a good structure. The pH is lower during the cooling process, just because when we decrease the temperature, some of the water become too solid first. So just left the buffer in the left waters. So the pH, so the concentration of the buffer increased. So the pH may also decreased. So that is very important. But just that is just we considered. We must perform the experiment to classify this point. The third, the influence of the mantle. We also consider this, but in these cases, the concentration of the buffer is the most important one. Through this formulation design, we get a successful product. Now this is the report. The case 5, adenoside for injection. This problem is collapse temperature is too low. This is not a very difficult problem to solve, but I just say it because of the temperature is too low. When the temperature is too low, we usually need to freeze dry the product in a very long cycle. Some class met this problem. They think that his freeze drying cycle is wrong, but usually it's not. When the collapse temperature is too low, we must control the temperature of the freeze drying below the collapse temperature, and freeze drying with a long cycle, just as this picture says. Now the cycle is very long. And last part, that is the 5 cases we talk about in our Tofflon Lyophilization lab. But usually we met some problems that is very difficult to solve. In the future, we hope that we can solve these problems more faster. So we would like to use another tools to solve these problems fast. It is a molecular simulation, just as this picture shows. These pictures are made by the software. The software is called GROMAX. Now this software is very good. It can simulate the whole freeze drying process. So when we don't know the intrinsic property of the drugs, we can use this software to give us some ideas. We want to know some intrinsic ideas of the drugs to give us a reference. Now this is a molecular simulation. This software is developed by a lot of scientists, so it is very good. We can analyze the H bond and energy of the drugs, of the whole freeze drying. So through by using these tools, it may give us a better freeze drying cycle. So that is the topic of mine. Thank you very much.